Okay, so as the first presentation in this reading group, I'm going to introduce several representative papers on inference functions, which is one of the most popular family of data attribution methods. So in this presentation, I will first give a high-level visual illustration of the inference function, and then we'll dive into the technical details, mathematical derivations of several variants of inference function implementations. And finally, we'll briefly see how do we evaluate the performance of inference functions, just to get a sense of it. So at a high level, the goal of inference function is to understand how do training data points, individual training data points, influence the model behaviors, right? So in a standard like machine learning pipeline, we have training data, and then we're training a model using this training data set. And then we have some test data. We make predictions on this test data point and do some evaluation, right? So when like maybe sometimes the model isn't performing well, we want to understand which individual training data points lead the model to make this prediction instead of that prediction. And this process of tracing back to the model behavior back to the training data points is so-called like data attribution. And how we can possibly do this, right? Below, I'm going to give you a great visual illustration made by Conway Ko. So let's think about this concrete application scenario where we have like a machine learning model and make predictions on a tissue patch containing human cells. And the goal of this prediction is to predict whether there's cancer in this tissue patch, right? So basically whether this tissue contains tumor cells, which are corresponding to cancer. So suppose for this particular test data point, and we have a learned model, it predicts that there's only 35 kind of likelihood that this cell containing a tumor, containing tumor cells. So basically, it thinks this is more likely to be a normal tissue rather than a cancer tissue. Now, suppose we know this is a wrong prediction. So this is actually a tissue with tumor cells. And also, suppose that the reason is actually there's one data point in the training data set, the third one, that is mislabeled. It's actually a like a tumor tissue, but it was mislabeled as normal. And also this cell, this image is similar to this image, so that misled the model to make the wrong prediction. Now, but we don't know like a priori which training data point is mislabeled. Our question is like, can we have some methods that can help us find out this mislabeled data point, right? So there's this classical idea called like leave one out approach, which can date back to like 1950s in statistics. The idea is very straightforward. So what we're going to do is to first remove one data point, right? This one, remove one data point from the training data set and retrain the model using the rest of this data set, right? So using this, the remaining training data points to retrain a model. Now we use this new model, we make a prediction on this test data point again, and we observe how much the prediction changes. And in this case, it's leaning even more towards like a normal tissue, but overall the change is very small. And we can repeat this process, removing the second training data points and retrain the model using the remaining data set and do this again, and we'll observe that, okay, this time the change of prediction is still very small. Then we repeat this for the third training data point, and suddenly we found that there's a large change on on the prediction in this newly retrained model, and also makes the prediction correct. So in this way, we know that, okay, this data point has a large influence on this model, on this trained model, on its prediction on this particular test data point, right? So that is a way for us to identify influential training data points. However, you can imagine that the problem with this approach, naively implementing it, is it requires repeatedly removing training data points and retrain the model, which is computationally expensive. So the solution to this problem is to have an efficient gradient-based approximation, which is exactly the influence function. To briefly get a sense what this approximation is doing, let's first introduce the weights on each data point. So basically, you can imagine we are instead of using the original, for example, average loss on all training data points, now we are inserting one scalar weight for each training data point. And when the weight is set to be all one, this is exactly the original training loss. Now, what we can do is if we set some of the weights, maybe one weight to be 0, so this is exactly as equivalent as removing this training data point, right? In this formulation. So with this formulation, we can now imagine that there's a mapping between the training data weights to the prediction of the trained model using these weights on a particular test data point. So that the output logic, for example, on a specific test data point. So given one set of weights, we can train a model using these weights and then see its prediction on a particular test data point. So there's a kind of complicated mapping from this training data weights to this prediction. So this mapping encapsulates the complicated model retraining process. So this is really a complicated function. But so let's focus on this function from the weights to the prediction. So basically, we can exactly we can exactly reproduce a kind of removal and retraining process without as this step without any approximation. So we basically just set the weight to be 0, and then we are removing one data point, right? And we can do this for the second weight and for the third weight, and we also observe the prediction will be changed. So the approximation we're going to do is to, instead of only allowing 0 or 1 weight on this function, now we allow that there could be a continuous weight for each data point, right? So we have a continuous approximation, and then we can calculate the partial derivative of this function with respect to this data weight. And moreover, we're going to evaluate this partial derivative at epsilon equals to 1, which is, you can imagine what this derivative is capturing is, if we do a small perturbation on one data point's weight, how much the model prediction will change, right? So this gradient is capturing that, evaluated at epsilon equals to 1. The benefit of doing this is that this gradient because it's evaluated at like kind of the original model weights with all one model weights. So it doesn't require any kind of model retraining on like new data set. We just need like some kind of gradient hashing stuff as the original model to obtain this score. And the idea of influence function is basically use this score as a kind of a proxy of the importance or influence of each individual training data point on the model behavior. So that is the high-level idea of influence function. Now we're going to dive into the details of the implementation and duration, and this is the main focus of this presentation, the second part. And this presentation is based on a list of papers shown here. So later, if you want to find out more details, you can refer back to this page and check out these papers. Okay. Now, the first thing we're going to do is to introduce some notations. And specifically, what we're going to do is to formally characterize the process of like the machine learning process with data weights. So machine learning with data weights. Okay. For some notations, let's say the machine learning parameters is theta. It's kind of vectorized parameters in d dimension. And the loss function is 1 over n data points summation wn, which is the weight for data n, and a loss function, for example, square loss or cross entropy as a function of theta. And we can denote this whole function as capital L, theta, and w. It's a function of both the parameter theta and also the model weight w, where this w is a vector of w1 to wn, and it's a n-dimensional vector. We'll also note like this 1 as all one vector. Okay. Now the machine learning process is basically trying to, for any given w, right, where we can learn a model parameterized by theta hat as a function of w. And what it's doing is basically by minimizing over theta L theta W. And we're also going to introduce several functions for notation convenience. Specifically, we're going to denote Gn theta as the gradient of Ln theta. And Hn theta is the Hessian. And furthermore, we can denote G, capital G, theta W as average over all the individual gradients. G and theta. And this also equals to the gradient of capital L theta W. And similarly, the Hessian H. So average over all the Hn theta. Oh, actually, missing Wn here. Okay. which is also the hashing of capital L. W, theta partial, theta transpose. Okay. Okay, so what we're going to see is that the original derivation of influence function is restricted to a strictly convex model. So for strictly convex model, we can write it as like the theta W can also be written as like it's equal to theta such that G theta W equal to 0, right? So for strictly convex models, we can, like, this is basically the first order condition of the optimality. And essentially, so this theta hat W is defined by this kind of implicit function, by this equation. So it's defined as an implicit function. We are also going to note that when W equals to an all-one vector, this is the original model, right? Basically the original model. And for notation convenience, we're going to denote theta hat 1 as theta hat 1. And also, we're going to denote the hashing 1 as the H function evaluated at theta 1 hat and 1. Okay, so this is a hashing of the original model trained on the full data set. And theta 1 hat is the parameters of the model trained on the full data set. Okay, so that's the notation we're going to need. Now, the derivation of influence function relies on this implicit function theorem, which is like a very basic theorem in calculus. So I'm going to write this theorem in the notation we just defined earlier. So to help you review this theorem. So we know like this G function is a function that mapping from Rd times Rn to Rd, right? And let's assume it is like continuous differentiable. And like for some fixed for some fixed value, let's just say like this theta 1 hat in Rd and like this one vector in Rn. Okay. Let's suppose there exists such a kind of pair such that G theta 1 hat 1 equals to 0, which is a 0 vector in Rd. Okay. Now, if partial G theta W partial theta hat evaluated at theta equals to theta 1 hat, W equals to 1, is invertible. Then the theorem states that there exists an open set U, which is a subset of Rn, and a unique function. Let's just write it as theta hat, mapping from U to Rd, such that theta W equals to theta 1 hat for any W in U. And also G theta hat W equals to 0. Right. So basically, when like this condition hold, which is true, like in your context of like strict convex model, it says that like this implicit function defined by like this G is unique, and we can write it down as like theta hat of W. So that basically maps any data weights to the model parameters. So like the function, the theorem is slightly more general, but like written in the context of our notations, it basically says this. And moreover, theta hat is continuously differentiable, and we can know the derivative of theta hat to W transpose. So this equals to partial G W against the first derivative, the first argument, so inverse partial G theta hat W against the second derivative. Okay, and in like in our notation, we can further simplify this as inverse H theta hat W inverse partial G theta hat W. Okay, so this is like what we can get from the implicit function theorem. Now, how is this relevant to influence function? So essentially, this thing is already very close to like the high level idea of influence function. Now, instead of like the influence of data points on the model behavior, on the model prediction, this is like the influence of the data points on the model parameters, right? So basically, if I perturb the data weights of particular data points, how much the model parameters is going to change. So this basically helps us first establish the influence of data on the model parameters. And specifically because we want to avoid the retraining, we're going to evaluate this partial theta hat W partial W transpose at W equals to 1, which is like the original data weights and model, right? So then plug in the formula, we'll get minus H1 inverse times partial G theta hat W partial W transpose evaluated at W equals to 1, right? So basically, the first thing becomes H1 when evaluated at W equals to 1. And then the second thing, we just like essentially copy it here. We can do like a simple derivation here. So recall that G theta hat W equals to the average over Wn Gn, right? So we can, for simplicity, we can first derive, see the like derivative over one single W over Wi, and with W equals to 1, right? Evaluate as W equal to 1. So for this derivation, like let's first for each term, let's take derivative over this W term. So then we get like 1 over n for Gi theta hat W. Evaluated as at W equals to 1. Plus, now if we take derivative over the G terms, then it becomes 1 over n summation n from 1 to capital N Wn partial to Gn theta partial theta evaluated at theta equals to sigma 1 hat. So this is a chain rule. And then partial theta hat W partial Wi. So evaluated at W equals to 1. And this can be simplified a little bit. So because this term, we can basically extract this term. So this will equals to N1 Gi. Here it's just C1. And so we can extract this term so that we can add a bracket here. And this one is essentially H1, right? So this is a derivative of, okay, it's a transpose. There's a derivative like of the gradient, which is a Hessian, and this is evaluated at theta 1, so it's exactly H1. So this becomes H1 times partial theta hat partial Wi evaluated at W equals to 1. Okay. Now, like, so this is for one term, for one I. Now it's not very difficult to see that the full gradient G theta hat W partial W transpose evaluated at W equals to 1. So like the full derivative would be like basically we just like stack the things, right? So it will be, so for the first thing, it's going to be a matrix over n column And for each column, it's going to be 1 over n gn theta 1, or n from 1 to capital N. Right, so this is the first term. And the second term is basically H1 partial theta hat W partial W transpose evaluate this W equals to 1, right? So we got the equation of let me see. Yeah, so when we plug in this formula back to here, we basically got an equation, right? So equation of this one. So we got the equation of like if you look at it, so if you plug in the formula to this one, then you got H inverse times H1 inverse times this, and H inverse times this, which becomes itself, right? So and also there's a minus sign. So what we'll get is like so basically it's 2 times this derivative will equals to minus H1 inverse times this, right? So we will get that this will lead to this thing. Solving the equation gives us equals to minus 1 over 2n H1 inverse. Again, this is big matrix over capital N columns, where each of the element is a Gn to capital N, right? So yeah, essentially it's like this thing. Okay, so this is like essentially how the data is going to influence the parameters. And specifically, we know this thing, right? So that's like the individual data points, theta W for one individual data point. Okay, evaluated as W equals to 1 as the original parameters. So this individual influence will be 1 over 2n H1 inverse Gn theta 1 hat. Okay, now our next question is like, because eventually, most times we are interested in how does the individual data points influence the model behaviors, right? Like usually it's a model prediction. So we'll introduce the idea of like a target function. So a target function, it can be very flexible. It's a function of theta. For example, it could be like a loss on a test data point. Like suppose we have maybe a regression model where like for example, let me see. If we have a regression model, And like the output of the model is like y hat x theta. Then like f theta could like be like on a tested point, the square loss on a tested point, which is y test, which is the label, minus y hat x test in theta, right? Square. So this is like a L test. You can write it as the test loss. Basically the loss on a tested point. So we can write it as L test, right? So it could also be a just the model output. For example, this is the first example. The second example is f theta will just be y hat x theta. Right? So this is like just model output. But anyway, so this is going to be a function on the theta. Then we can investigate the like the influence of each individual data point on this target function. So we're going to write like partial f theta w, partial, let's say just like a single one, wn, evaluated at w equals to 1. And by a simple chain rule, this will be equal to f theta partial theta transpose evaluated at theta equals to theta 1 hat times partial theta hat w partial wn evaluated as at w equals to 1, right? And in this case, like let's say, for example, if our f theta is L test theta, so this will be just partial L test theta partial theta hat theta transpose, and theta is theta 1 and times 1 over 2n h1 transpose, like what we have earlier, this one, gn theta 1. And we may also like, we can like generalize the definition of G a little bit. Then we can write it as G test, right? So this one is essentially G test evaluated at theta 1. And we can also like move this to the front. H1 inverse G then theta 1. So basically, when the target function, when f is L, like when the target function is L test, then the influence of each individual data point on the loss function on the tested point can be written as this formula. Right. And this like can have an interesting interpretation because we observe there's a kind of a symmetric structure for this thing. You can also view it as we have an inner product, like another interpretation. So we have an inner product over G test and Gn, where like with the kernel H1 inverse, right? So you can view this as we are kind of measuring a similarity between the test data point we're interested in and a training data point n. But we are first projecting them, this data point, into a feature map defined by the gradient of the parameters. And then we're measuring it, we're measuring the similarity with this inner product defined by this H1 inverse, the Hessian inverse. So that's another way to kind of to view this particular influence function. Okay, so up to this point, we've obtained the general formula of influence function, which is approximating the kind of data removal and retraining process, but without any retraining, right? So because like all these things are evaluated at sigma 1 hat, which is the origin model. However, in practice, there's this is still challenging to calculate, mainly because this Hessian inverse, and specifically, like there's this Hessian inverse times gradient. It's like this term. We call it like inverse Hessian vector product. So this and this is like there are a few problems associated with this the calculation of this one. So first of all, like although like in previously we've all in the derivation of influence function, we have assumed that the model is strictly convex, and so that the Hessian is invertible, right? But in practice, for example, when we have like neural network models, like this H may not be invertible. So H may not be invertible. So can we still apply influence function on those models, those kind of neural network models in this case? In practice, the answer is actually yes. So there are a lot of different efforts trying to mitigate this problem to generalize the influence function on non-convex models with singular Hessian. But like I'll just mention, like the simplest trick people find useful is to make Hessian to basically add a like small damping factor on the Hessian. So make Hessian from H to H plus lambda I for some small lambda to make this small like positive lambda to make this invertible, so that we can still calculate like this term G test Hessian inverse G n, right? So so that we can still calculate this term, and we'll just use that as influence function for this kind of more complicated models. The second problem is actually the second and third problem are all about like computation cost. Like note that H is a matrix of D by D. So like if D is very large, so like if D is large, like for large D, like this is like infeasible. I mean, that is very expensive, right? So that's the so this is very expensive to calculate the Hessian inverse. And the third problem is the Hessian is over all the n training data points. N data points. And for large n, there will be both like memory issue and also and also like the computing cost is very high, right? So like for large n, it's also very expensive. So these are the kind of practical problems we face when we are trying to generalize this inference function to large, complicated like neural network models. And what I'm going to show for the rest of this part is basically methods that try to make this process efficient. At a high level, I want to mention like basically what's a kind of potential way we can mitigate this. So we observe that like so this term H inverse G, it also appears in some other like problems. For example, like solving linear systems, right? So some solutions to kind of efficiently solving linear system can be used. For example, conjugate gradient. Like CG. So you'll see like inference function based on CG. But the problem is that like in this case, it still doesn't solve the like this third challenge over like the H is over n data points. Like so for CG, like it's not like trivial to kind of extend it to kind of to a stochastic a mini batch setting. So that's a problem. Unfortunately, like this H inverse G also appears in a lot of like second order optimization problem. So for example, Newton's method, right? You will see this kind of H inverse times gradient. So in this kind of second order optimization, especially for neural networks, there are tons of literature trying to like solve this kind of computation problem. So many of the following work are actually inspired by the second order optimization literature. Okay, so the first one, like this first method is called LiSSA, which comes from like this paper for a second order optimization. So the idea of LiSSA to accelerate the inverse Hessian vector product problem is that we can define like a sequence of quantities Hj inverse. So this is just a notation. The whole thing is a notation. It's defined as summation over from I from j 0 to j I minus h to the power of I. So we're here h is the Hessian. And under some regularity assumption, like this is actually a kind of like Taylor expansion, like expansion terms. So like we know, okay, sorry, the limit of this term. Like this approach, like the true, like the approach the original like Hessian inverse. So because like this is essentially like the Taylor term of Hessian inverse. We can also equivalently define Hj inverse recursively. So define this term recursively. Write Hj inverse equals to I plus I minus H, Hj minus 1 inverse. So while this thing itself now doesn't solve the problem of the larger n, like recall h is like 1/n summation from 1 to capital N, a Wn h. Okay. We are talking about like when W equals to all 1, so we can simplify this a little bit. Like Hn theta 1 hat, right? So this is H, right? So if we directly use this recursion, like we still need to calculate H, which is doesn't solve the problem. But what this definition this Hj inverse offers is that we can do a stochastic estimate. So let's H bracket 1 tilde, H2 tilde to Hj tilde as independent samples from this set, right? Hn1 hat. So basically, like for the Hessian on individual training data points, like this is a set of Hessians on the individual training data points. So let's this quantities as individual independent samples of Hessians on individual data points, and then define H0 inverse also tilde as the identity matrix, and then recursively HT inverse tilde equals to I plus I minus HT tilde times T minus 1 inverse. So here we are defining another sequence of this kind of HT inverse with a tilde, where so this is an estimate of this sequence, but now we are using like a random sample of individual Hessian instead of the full Hessian in defining this, right? And then it's easy to see that the expectation of this H tilde J, let's say, equals to Hj inverse. So this gives us, so like basically the definition of this H tilde inverse sequence is an unbiased estimate of the original sequence, right? And this helps us to like alleviate the kind of calculation over the full data set problem, because now we don't need the full Hessian H, we just need the individual ones, right? And furthermore, another benefit of this, for the sake of like calculating the IHVP, which is like suppose H1 like H1G, H minus H inverse G. We can define RT as like the estimator, the stochastic estimator HT inverse times G. And this equals to, basically, we can plug in this formula here. So like equals to G plus I minus H P tilde. And then like this thing times G becomes RT minus 1. Okay. And simplify it a little bit more, it's like G plus RT minus T minus 1, RT minus 1, minus H tilde T RT minus 1. Okay, so we can have a recursive definition, like which is kind of a stochastic estimate for like the original H inverse G, right? And for this recursive definition, one benefit we can leverage is that we don't really need to actually calculate each of this Hessian matrix. Like although this is just for one data point, that's like calculating the Hessian matrix because it's a D by D matrix. It can still be computationally expensive. We can further reduce the computing cost by leveraging this the trick of like Hessian vector product. Or IHVP. So we can leverage the fact that calculating the Hessian times the vector, like this can be done efficiently through an algorithm with similar cost. As one backward. So basically this has similar cost as calculating the gradient, like instead of the Hessian. So we don't really need to explicitly calculate Hessian to obtain the Hessian vector product. So this is nice, right? So this solves the like the problem of calculating over like it doesn't require do explicit inverse, and also it doesn't require calculating over all the n data points, and it also kind of even avoided calculating the Hessian explicitly, just using IHVP, the IHVP trick. So this is like reasonably efficient, but still in practice, like there are still kind of two limitations. First is like J could be large to be accurate, right? So note that like this approximation of HJ inverse to H inverse, like this is like in the limit of for J to the infinity, and in practice, J could be required to be very large to make this approximation accurate, right? So and this will propagate through to all the way to this kind of RT, right? So we need probably a very large T to be able to accurately approximate this original IHVP. This is one limitation. And also this is kind of recursive, so we can really parallelize it to accelerate the calculation. And the second limitation of this approach is this process, the whole process needs to be repeated for each new vector G, right? So because we didn't like explicitly get the HT and stuff, so for each new vector G, we essentially need to repeat most of this process. So that's also caused some kind of practical challenges when we have a lot of data points. So that's the caveat of this LiSSA method. And then there's this Arnoldi method, like Arnoldi-based inference function. So the idea of this method is quite straightforward. So we know, like, if we can do eigen decompositions, right, of H of the Hessian. So suppose we can do eigen decompositions, U decompose H as U transpose, right? So this is a diagonal matrix. This is eigenvectors, and the H inverse would be U lambda transpose, lambda inverse U transpose, right? So if we know the eigen decompositions of H, then of course this problem of H inverse will be very easy, and also calculating the the Hessian, maybe the Hessian vector product will also be easy. Like basically, like for a G prime H inverse G, you just need to first project G to the eigenspace, G and G prime to the eigenspace, and then like weighted by this kind of inverse eigenvalue. So that's like this calculation will be very efficient. But of course, we know that doing eigen decomposition itself is kind of as expensive as doing like the matrix inversion, right? So we can't really directly do that. But there's like this kind of classical approach of so-called like Arnoldi iteration, which is an efficient approximation of dominant eigenvalues and eigenvectors of H. So the idea is that if we can have an efficient way to get the several leading eigenvalues in this lambda and their corresponding eigenvectors, right? And then maybe we can just like use that to approximate this original Hessian inverse and vector product. So to just give you a rough idea of why what this Arnoldi iteration is doing. So it's constructing something called like Krylov subspace, which is like for like Km. This is defined as the span of a vector B, like this is an aperture vector B, and HB, H squared B, all the way to H minus M minus 1B, right? So we know that like for this thing, right, HKB, so this will approach the largest eigenvector in the absolute sense as K goes to infinity, right? So we know like this, like matrix matrix power, we can obtain its largest eigenvector. The idea of this Arnoldi iteration is that the also normal basis of Km can be a kind of a good approximation of the top eigenvectors. Can approximate the top M eigenvectors of H. So that's the idea. And so this kind of Arnoldi attribution method will, like by constructing this space, right, it will give us a kind of efficient way to approximate the top eigenvalues and eigenvectors. And another thing to note that is like these calculations, like the construction of these vectors can also be obtained by IHVP, right? So we don't really need to explicitly construct H. So that's a kind of rough idea of this Arnoldi based method to efficiently solve inverse Hessian vector product. Okay, now we're going to move on to another method. So this is also something coming from like second order optimization. It's something called like natural gradient descent. So the idea of that is we are going to use something to replace the Hessian originally when doing like second order optimization. So instead of like H inverse G, we're going to replace it with a matrix Fg, F inverse G, where F is the Fisher information matrix. So it can be written as X expectation sampling X from data and Y from the model, actually, parameterized by theta. Where the thing we're going to take in expectation is like the score function or the gradient of the log probability P Y. Okay. Let's write this way. This is a conditional probability Y in X theta partial theta and so this is a definition of this Fisher information matrix, and it can also be written as a like empirical. Like another version of it is to kind of treat this as the empirical distribution, which will then equals to 1 over n summation over all the data point and taking the expectation just over the label. Actually, the label sampled from the model this partial log p partial theta partial log p partial theta transpose. One note is that this expectation like for some, depending on the model, right? If in the machine learning model, for example, if it's a classification with a softmax output, so like the closed form expression for this expectation often exists. So while it's written as an expectation, but for some for certain py given x parameterized by theta, we can evaluate it because the closed form exists. And there's another thing that is relevant to it is something called like empirical feature. So another matrix called empirical feature, which is defined as 1 over n, summation over n, partial log p y in x, zero, partial log p x. So the difference between this empirical feature and the feature is that like the nuance is here. So for this one, for this y, so this is actually sampling from like this model, right? So okay, we should write it here. Like in the empirical version is here is xn. So basically, so this is for each data point, but this y is not the label of this data point n. Is instead a pseudo label. Like we are sampling from the like model, maybe softmax output of the model, right? But here in the empirical feature, we're directly using the real label at yn. So the real label associated with the like the data point n, x and yn. So that's the major difference. When like in the original like natural gradient descent, we should really use the like the feature instead of this empirical feature. But in the case of instance function, because we are always evaluating at theta 1 hat, right, as a like learned model. So this like real label usually are having high probability at this model distribution, like especially for complicated models like neural networks. We usually like will overfit the training data, right? So this real label will very often appear as like if you sample from the model, right? So in this case, this two, because the pseudo labels and the real labels become similar. So in practice, like this empirical feature and this like the real expectation feature, they are not that different. Like just for the purpose of in calculating like influence function. Okay, so that's one note. Another note is that both of this definition, this true feature and empirical feature, they are always positive semi-definite, right? So even for even if your model is neural networks, because of what their definition is in this form, so they're always like positive semi-definite. So in practice, that means it could be like more numerically stable. And when you are adding a damping factors, you could add a smaller damping factors to make the matrix like invertible. So and this like in practice enables some method to efficiently calculating the influence function if we substitute this h with f with the feature. So one such method is called like EK-FAC. So the idea is to approximate f inverse by like it's specifically designed for MLP model. So it's to approximate F inverse by leveraging the structure of MLP. The reason we still need to approximate this F inverse is like by just substituting H inverse with F inverse doesn't automatically solve this problem because F is still kind of like a D by D matrix, and it's still calculating over all the n data points. So this doesn't like automatically solve the problem, but it allows us to do some like other approximations. And here's a K-FAC. We need to first establish some notations, like first denote. Because we are going to calculate the gradient, we're going to look at the gradient for different part of the model parameters. So let's just denote like this V bar as the gradient of log probability over V. Okay. And so we can simplify F as the expectation over like theta bar transpose. So in the K-FAC, the first approximation we are going to have is like we look into the different layers of this MLP, the fully connected neural networks. So like suppose theta, there are L layers of the MLP. Like we can decompose theta from theta 1 to theta L. And what we're going to assume is that the assumption we're going to make is that theta K bar is independent of theta L. Okay, so the independence is because like this theta bar here, they are actually random variables because we are sampling. They depend on the random sample of Y. So by making them the assumption that they are independent, then this F matrix will have a block structure. So we are assuming like they're independent for all the K and L that are different. Then F will have this block structure, F1 to FL. Right. That's the first assumption made by this K-FAC. The second assumption is a little bit more complicated. So we're going to look into the detailed structure of the MLP. Let's first say the theta L is the vectorized version of WL, where WL is in R is a matrix. So basically, it's a parameter matrix of the MLP layer, maybe including the bias term. Is DL2 times DL1. So it has input DL1 of size DL1 and output of size DL2, right? And then essentially like theta L is of size DL, where DL is DL1 times DL2, right? Like theta is a vector double submatrix. And for the MLP, we denote SL equals to WL times A L minus 1 and AL equals to sigma SL. So SL is the logit for the neurons before activation. Theta is the activation function, and AL is the basically the neurons after activation. Then we know that like the gradient with respect to W, which we denote WL bar, will equal to SL bar. So that by chain rule, right? So the gradient with respect to SL times AL minus 1 transpose. So this is the gradient of WL. And this can be written when written in terms of theta L, like the vectorized form. It can be written as theta L equals to A L minus 1 times SL bar, where this one is the Kronecker product. So we can write FL as expectation over theta L. So transpose. So FL is like one block of the F corresponding to layer L. And this equals to by some like simple algebra, this will equals to AL minus 1, AL minus 1 transpose, Kronecker product, SL bar, SL bar transpose. Now we can define this one as AL minus 1 and this one as SL. So this is like a capital S. Well, this is like a like this is like a smaller S. Then it will equals to essentially like expectation A L minus 1 Kronecker product S L. And another assumption made by this K-FAC approximation is that we are assuming this A and S are independent. So assume they are independent. So, oops. So that gives us like expectation. So this is assumption A L minus 1 expectation SL. Okay. So that's significant. With these two assumptions, we have significantly simplified kind of the F, or basically we embedded like a very detailed structure of the F. And our observation is that these two, if you look at it and like their definition, so they are these two are uncentered covariance of this AL minus 1 and SL. So they are uncentered covariance. So these two terms, these two terms can actually be like estimated by just sampling. But by just like sampling over like from the kind of distribution. So yeah, so the idea is that instead of like using the full data, we can estimate the things by independently sampling and then make independent estimate and get estimate like a L minus 1 hat and SL hat. So that's the idea. And finally, we will just like use this estimated AL minus 1 and SL to approximate this FL and also like this F. Okay, now given that we have had this estimate of each block of this F matrix, which is like a L minus 1, to repeat it here, SL estimate. The calculation of this inverse Hessian product at each layer F will be, let's say we have GL, which will be the gradient vector corresponding to the layer L, right? This will be AL minus 1 SL inverse GL and could be written as AL minus 1 hat inverse SL by the property of a Kronecker product GL, and it can be further written as AL minus 1 inverse unvac this GL and SL inverse. So here this unvac means reshape the vector GL to match the size of the WL. And here vectorize is like a further vectorizes this whole matrix. So in this case, we will just directly do matrix inversion for this two. And the point is, the original F matrix is like dimension D times D, and the F hat is of dimension DL times DL. Well, AL minus 1 has dimension DL1 times DL1, and SL has dimension DL2 times DL2. So, and we know DL equals to DL1 times DL2. Well, D equals to summation L equals to 1 to capital L DL, right? So now instead of like directly inverting F, we can reduce it to, by assuming this kind of Kronecker structure, we can just invert this two matrix, a sequence of this two matrix, which is much, much smaller than the original F matrix, and also it's also much smaller than the F hat, right? So this is a benefit brought by this assumption of this Kronecker product. So we can solve this inverse Hessian vector product problem more efficiently. Well, this is like designed to be applicable only for MLP neural network models. In practice, we can also apply this method by restricting the calculation to MLP layers only. So basically, we're having another assumption that all other parameters other than MLP layers are fixed in calculating the influence function. But because the parameters of the MLP layers are, for example, maybe in like in models like convolutional neural network or transformers, the majority of parameters actually came from the MLP layers, right? So in that case, like this kind of approximation still works reasonably well in practice. And finally, there's a minor, not minor, but a small correction on the K-FAC to make it work better. So recall that like for K-FAC, we are making an assumption like this A Kronecker product S. I'm omitting the like subscript. So we are having this assumption, right? So like assuming they're independent and then approximates this expectation as the Kronecker product of the two expectations. Now, of course, this will lead to some approximation error. And in this like EK-FAC, basically we're doing some correction to reduce this approximation error while still having the calculation efficient. So the idea is we can do eigendecomposition for this matrix, for this like expected matrix, like assuming this equals to QA lambda A, QA transpose, and similarly this equals to QS lambda S, QS transpose. So this is eigendecomposition of the whole expected matrix instead of like the A and S. Now, this thing, EA Kronecker product ES will equal to, so this is also a nice property brought by the Kronecker product. So equals to QA QS lambda A product lambda S and QA product QS transpose. So what EK-FAC is doing is basically to replace this lambda A Kronecker product lambda S, which is a diagonal matrix, which is still a diagonal matrix, by something else, by another diagonal matrix, lambda star, that is like DL times DL dimension, the same dimension as this one, and also diagonal. Diagonal. Okay. And such that like this lambda star minimize, so it's arg mean over lambda, minimize the difference between the original thing we want to approximate and QA QS lambda QA transpose. So lambda star is the lambda that minimize like this difference between this thing and the original quantity we want to approximate, right? So in this sense, like when we replace this thing with lambda star, it will lead to a better approximation. So that's that's why it's called like eigenvalue corrected K-FAC, so EK-FAC. And this can be done efficiently as lambda star has a closed form solution. Where each element equals to expectation of QA, QS, and theta L, and the whole thing. Right? So it's like like this has a closed form solution that equals to the variance of this term. So this lambda star is also easy to estimate. And also it's easy to store because it's a diagonal matrix. So it doesn't like increase a lot of computation cost. And similarly, like this structure, when we have it in this structure, when this is replaced by lambda star, like the calculation of the inverse Hessian product, inverse Hessian vector product can also be made pretty efficient. So that is like what is usually used in practice to calculate the influence function by using this EK-FAC. Finally, another method that is proposed recently is kind of relevant to this Fisher implementation of this kind of Hessian inverse product. So recall like the empirical Fisher, which is we mentioned earlier. Empirical Fisher. Which is like 1 over n summation n equals to 1 to n. And it's a log likelihood, it's a gradient of the log likelihood, which can also be written as like when we are, for example, doing classification using partial entropy loss, which is also the loss, which is also the gradient of the loss function, right? So we will just write it as here for to simplify the notation. Transpose. So this is an empirical Fisher. And in practice, this is usually, we usually have a damping factor for a non-convex model. So we will have like a lambda here. Now, suppose we want to do this kind of inversion, right? What we can do is to, when we are inverting this one, like in this DataInf method, so they did an approximation like this. So instead of like inverting this whole, they are exchanging the inversion and the summation. So they're doing something like this. So they are doing 1 over n, summation n from 1 to n. Partial ln, partial theta, partial ln, partial theta transpose. Plus lambda I and inverse. So they use this term to approximate like the original inversion. And what's nice about this term is that this is a rank 1 matrix. And this whole thing, plus this identity matrix, this whole thing can be simplified by like the Sherman-Morrison formula. Which has a kind of closed form solution and is pretty efficient to calculate. And in practice, we can also kind of do this blockwise, right? So basically do this layer-wise. So we can like just do this for each within each layer of parameters by restricting the gradient to the gradients to that layer. So this is something we can do in practice. And this turns out to be a this approximation is good for when the parameters itself has low rank structure itself. So it's particularly good for like LoRa parameters when you do this kind of low rank adapter training, fine tuning. So this is another way to kind of also for some specific model structure, especially for LoRa fine tuning, you can do this kind of inverse Hessian product more efficiently. And also, like you can use this to calculate the inference function more efficiently. Okay, so those are several representative works that try to derive like practically feasible inference function implementation. And finally, I'm going to very briefly mention how can we evaluate, how should we evaluate the efficacy of inference function, right? And I would say there are two types of evaluation. Like one is application agnostic and another is application driven. So for application agnostic, there's one metric called like is basically comparison with leave one out retraining, right? So the evaluation could be pretty expensive. So basically, recall at the very beginning, the goal of the inference function is to approximate the process of removing a data point and then retrain the model and observe the change of prediction. So the inference score basically capture that change of, is a proxy of that change of prediction. So to evaluate the efficacy of the inference scores, what people did is we do some leave one out retraining, right? And we observe like the actual difference, like in the loss function or in the prediction, and also like the influence score, right? So which is a predicted difference in the loss function, and then like compare these two, and usually through rank correlation to basically see if the order of the importance is the same in terms of influence function score and the actual leave one out retraining. And for example, this figure comes from this Cohen-Leung paper, which here it plots like this kind of comparison on several different models. Okay, so this is kind of like application agnostic. It goes from the original goal of influence function, definition of influence function, and then just measure it. And there's also another popular type of evaluation metric, which is application driven. For example, in our motivating example, we are actually having some mislabeled training data, and we want to find it out, right? So it's that cancer example. So so basically, this like the mislabel detection is also a popular evaluation metric for influence functions, where given a training data set, and also you train the model, and you can calculate the influence score. And specifically, you calculate the influence on like something called self-influence, means that for each training data point, you calculate the influence score of this training data point on the prediction on itself. So basically, instead of like G test H inverse Gn, you calculate Gn H inverse Gn for each n, right? So you call this self influence. Of course, there's like some normalizing constant. So you use this as a so-called like self-influence score, and you find like so you compare the self-influence on all training data points, and if like there's some like self-influence in absolute value that is super large, that means that this training data point is super influential to the predictions on itself. And if you remove this data point, the prediction will change a lot, right? So that usually means this is a kind of outlier data point in the training data set. And you just use that as a heuristic to flagging mislabeled data. Because like if this data point is very inconsistent with the rest of the training data set, then it is more likely to be mislabeled. And you can have a training data set that you manually mislabel some data point, and then you use this self-influence to predict which one are mislabeled, and then you can calculate the kind of prediction accuracy of this kind of mislabeled data points. So that is like a more application-driven evaluation metric. And there are more evaluation metrics. As you can imagine, understanding the importance of training data points is kind of like it could be defined in different ways, right? So there are actually a lot of different evaluation metrics proposed in the literature, but here I'm just listing two of like the two of probably most popular ones to give you a sense how one may evaluate the effectiveness of influence function. In our later meetings, we probably will see more like more recent and other evaluation metrics as well. Okay, so that wraps up like the first presentation. Thank you.